Okay, I hope everyone can hear my voice clearly. Okay, if there is something wrong uh, in my voice, let me know. The speaker is not working, let me know. Okay, we can start now for the notes. So today I will continue on chapter 14, and hopefully the screen can be clearly seen. I think it's a little bit delayed from my writing, but still okay. I think it's just like really uh, maybe 0.5 seconds delay, but I think it'll be okay. Okay, I think we can start by reviewing what we have done, at least from these two examples, how we can derive a function of two variables. Okay, we can derive partially. So the writings for partial, we are going to have f and then x like that, or f and with y like that. Now this is symbols that we are going to use for partial derivative. Okay, it means that we are partially derived with respect to x and the other one with respect to y. Okay, so we are going to treat each of variable as a constant. Okay. Now, from here, what I want to move on is that because we have partial x and partial y, now because we have partial x and partial y, now these two partial symbols, they symbolize that for function that has two variables, we will at least have these two partials, right? But how we can make these two into our visuals? Okay, how to imagine? How to visualize? Okay, now remember that if we have z, or our function we can write as z, so it means that this is a surface represent a surface. So the functions, rather instead of curve, just a curve, we will have a surface that we are already defined in the, I think, in the introductions and in 14.2 what kind of surface that we might have. So when we deal with this surface, then we are actually dealing with at least two tangents. Okay. So tangent, they are having two tangents because of we have partial x and partial y. Okay. So how to make it into our understanding? So the blue, or it seems a little bit purple, this is the surface. Okay, the surface S, and imagine we are having two curves, C1 and C2. C1 and C2 that is crossing this surface S. Okay, so we are having the C1 and C2, and then at some point, okay, for this example, at point P, we are going to have, for C2 we have a T2 tangent 2, for C1 we have T1. Okay. Now I hope you still remember when we deal with limit. Okay, when we deal with limit, the limit of function of two variables, of course we can imagine how we can approach the point from many paths, right? If you remember, we have this limit. Okay, it means that we can approach from every from everywhere within the domain, right? Within the domain. Okay. Now, as an implication for this limit is we are going to have the path, right? The path that we can set up. The path can be line, can be some line equation, maybe y equals 0, y equals 1, y equals 2, depends on the case. For example, in our case here, for 0, 0, or maybe let me write as AB, make it more general. So we can make x equal a as a constant. So x is constant and y will be our evaluation. And vice versa, we can have y as a constant and x as output variable. And by doing so, we are actually doing, or we can correlate those limits with the partial derivative, right? And as an implication of those equations and partial derivative and from limit also, we can write that if we are going to approach this point, okay, we are going to approach this point P, okay, we can approach from anywhere, right? We can approach from, for example, from here, a little bit delay, okay, and we can approach from this part, and we can also from this part, right? But then, to make it more concise and precise and to be adjusted in a structured models, we are going to have C1, curve 1 and curve 2 as our path to approach this point. So we are going to approach this C1, P with C1 and another curve C2. Okay. So I hope you get my point of view from here. And then from here, we are going to have, if, okay, y equal b, this is what I've said before, we restrict observation to only curve 1 C or C1, and if x equal a, we are restricting observation only for C2 or curve 2. C1 and C2, they are both passing through the P. Okay. we can write the C1. Maybe we can make the graph a little bit higher, and this a little bit higher here. I think better to write here. So C1, we are going to have, let's say we have a function g, okay, in which we have function f, and then y is equal to constant b, and we are going to have partial derivative with respect to x. Okay, so we have t1 g prime at a, okay, because it's the point that we are going to make it's at a. So the partial x ab. Okay, so this means that it's partial x. And we have another t2. Let me write with other function h. So g and h is a function of single variable of function of two variables, and the other variables becomes a constant. Okay, I hope you don't get confused on that point. So we can write f, and then now a, and then y, meaning this will be constant for x, and y will be our variable. Okay, and this will get the idea for the tangent is h prime of b. And thus this defines our partial derivative with respect to y of point A, B. Now the partial x and partial y we can interpret these two partials as the slope. So let me write here, interpret as slope of tangent. Tangent lines at P to the traces C1 and C2 of C1 and C2 of surface S in planes y equal b and x equal a. And we can define or write the partial x in terms of, because we make z, okay, as our function of xy, right, from here. Then a partial x and partial y we can write down as dou z dou x and dou z dou y. or we can also add that this is slope in x-axis direction. This is slope in y-axis direction. So before, when we have only a curve, we define the tangent easily from the curve, and then we can run linear equations. Very easy to be translated into equations from the visuals. Now we have 3 dimensions. I think still can be visualized, not really that difficult. But then, if you have more dimensions, that will be very difficult to visualize. Okay? Although in calculations, or if we look on the formulations, it's not that complicated for calculations. But in terms of how we can see as an object, it will be difficult if we have more dimensions. But for now, it's still okay. For now, it's still okay. Okay. Now let me give you a few examples to let you get through some familiarity in partial derivatives. Yeah, I hope the notes clear enough. And I think if you have problems to take notes when you are in a class, I'm suggesting not take all notes. Take I think just the important points, and you can add other points that I think maybe you think that you need to write later. You can write later. So you can write now just a few points that you are thinking that, okay, this is important. You can complete your notes when you review. Okay, so I'm suggesting to review the notes by looking at the videos of the recording, like the recording. You can watch, and maybe you can skip some parts and then go to part that you are really concerned with, and you can take notes from there. Okay, because I believe some of you are still thinking that you need to write notes all the time when you have class with me. Not at all. Okay, so you can take notes, like just a simple notes first, and then you can write which one is the most important essentials on the class, and later on you can complete your notes by reviewing. And by reviewing means it doesn't need to be watching from the beginning, but you can watch just a point that you are really concerned with. Okay, I hope this method can help you. Okay, can help you, because if you think that I'm teaching like taking the page too fast, uh, I try to slow my notes and take times for you, give times for you for some note taking, but I will not be really efficient. Okay, my suggestion. Okay. So you can take a few important from this note, and then you can complete later. Okay. Okay. Now let me give you more context on our subject. Let me give you a function. Okay. Now the functions that could have appear on the partial derivative is a function that is probably from your chapter 12, the quadratic surface. So we know that we can write this as SC equal 4, right? And we can imagine that this is having a parabola and another parabola, and then it has xy has it can become an ellipse, so it will have parabola because it's negative, and it will be having an ellipse here, so it's an elliptic paraboloid. Okay, now if we are going to find the partial x at one point, at 1, 1, x equal 1, y equal 1, and partial y and then if we are going to observe in geometric or in visual how we can interpret this partials. First, what we can do is we are going to take the partial x okay. Now from the functions, or let me write the functions once more time. Okay, that's the function. So partial x means that we are going to treat x as our only variable, and the other part will be a constant. So we are just having minus 2x as our partial x. Okay. So when we have partial x at 1, 1, then it will be minus 2. Now same thing for partial y. We are going to have only y that is that will be our variable. This will be minus 4y. So partial y at 1, 1 will be equal to negative 4. Now if we are going to translate these numbers into our graph, okay, if we are going to look how this paraboloid behaves, first let's see our point 1, 1, 1. Okay, that is our objectives. We are going to evaluate the partials on that point 1, 1, 1, and notice that you have two curves as your path, C1 and C2. And C1 we are going to have the y equal 1 as our plane, and this will be the slope, the first slope, and then C2 this will be the second curve, and we have also the second slope. we have the x equal 1 as our plane, or plane. So what does the this units means? What does it mean? It means that minus means it will be decreased. Okay? So it means that the z decreased 2 units. And this means that z decreased 4 units. Z decreased 2 units for every increase in x. This is in y. Okay. If I give you the x cubed plus y cubed plus z cubed plus 6xyz plus 4 equals 0. Okay. If z can be defined or is defined implicitly as a function of x and y. So we can actually using the implicit differentiation and for this case that if it is having 3 variables, we can take implicit approach and take z as implicitly for both x and y. So we are going to evaluate the z over the x and the z over the y. So evaluate both of this at the question is so to find dou z over dou x, then we are going to differentiate implicitly as a function of x and y. With respect to x, sorry. with respect to x, and y is a constant, and z as function of x. So what the implication from these wordings? So basically, it will be similar to what we have done in implicit differentiations, but now whenever you see z, you need to derive z with terms of dou z dou x. Okay, let me write down the function or the full equations first. Okay. Now first we differentiate with respect to x, right? So first x is similar what we have learned as in derivative. So we're just having 3x squared. Now how about the y cube? Y cube we treat as a constant, so it will be 0. So this will be resulting 0. Okay. And z is a function of x. So we are going to differentiate z, 3z squared, and write down dou z dou x. I hope you still remember on the implicit differentiation in calculus 1. We are having x, y, and then we differentiate with respect to x and treat y as a function of x. So we are going to write differentiate of y as dy over dx. Okay. And then what will happen with this x, y, z? Now we have two functions here, x and z. Okay, because z is function of x in this term. So we are going to have a product rule. Okay, product rule. So we are going to have plus 6yz, because x is differentiated to 1, and then 6xy, z becomes dou z dou x. Okay, finish this. Or maybe let me cancel all with this. So okay, we'll have z squared plus 2xy, and this will be equal to minus x squared minus 2yz, and we can write down that's going to be our equation for dou z dou x. They make it a little bit smaller, and we can input the point. Okay, so this will be equal to negative 5 over 2. Okay, now the other one, the dou z over dou y. Okay, now we are going to treat x as a constant. So this will be 0, and this will be 3y cubed. And now we have 3z, y cubed. Should be squared. 3z squared, dou z over dou y. And similarly, this will be plus 6xc plus 6 xy dou z dou y. So same way we have z squared plus 2xy and equal, this will be y squared plus xc, 2xc. Okay, now we finish the implicit, and then don't forget to plug in the value that we are going to find. And this will be 4 minus 2 okay, this will be 3 1 plus 2 is 3, 4 minus 1 minus 2 is minus 1 is 2, yeah, 3 over 2. Okay, I hope this implicit is not really a problem. Yeah, I hope, because it's mirroring, or it's reflecting the calculus one that you have studied. Okay, I hope it's understandable to find the dou z, dou x, dou z, dou y from function of 3 variables. Okay, from function of 3 variables. Okay. Maybe any questions so far? Any questions? Anything that you are maybe a little bit confusing? Okay, if there is no questions, let me continue. Continuing to the general forms for partial derivatives. Okay. If we have more than 2 variables, or maybe more, and more, 3, 4, 5, and what we can do to simplify the forms. So function more than two variables. Okay, if a function f is a function of three variables, x, y, and z, then the partial derivative with respect to x or fx is defined as, we are going to write the limit definition. Okay, basically similar approach. Okay, we have partial y, partial z. Then if we define a new variable w as a function of three variable x, y, z, okay, x, y, z, then partial x we can write as dou w dou x, or this is symbolized or we can interpret as rate of change of w with respect to x. While y and z are fixed or constant. But can we draw this? Can we make visuals? Not that easy. It's not easy, and it's a thing for now. We cannot visualize this into graphs because it's on four dimension. If it's on 3 dimension, we can easily write down x-axis, y-axis, z-axis. Imagine in a space, right? And then we can make it some models, some surface, or even 3-dimension models. Okay, but this one, the functions of 3 variables, we have limit in how we can translate into picture. I think this is very difficult. But in terms of writing word equations, we can write more and more variables. So if we have 4, 5, 6, we still can take it partially. We can take the partial derivatives, okay, but we cannot translate those equations into a graph. Okay, so in general, if u is a function of n variables, so it can be any variables. So we can write u is a function of, let's say, from x1, x2, x3, x4, until xn. Then its partial derivative with respect to the some number of variable, let's say I variable, xi is, or we can write f xi. Okay, you can write in general the limit definition as that. Or we can write different symbols. So you have, if you have more than 2, 3, 4, in practice, you can differentiate using partial. I think it's not that difficult. If you learn how to practice and familiar with the equation, it has a patterns that you can. I trust you can build on those techniques. Okay, so whenever you have example, okay, for example, you have function of 3 variables. Partial x, we can find partial x, we can find partial y, we can find partial z, which means that partial x refers to the variable will be x. Okay. The other will be a constant. So we will have, with just x as variable, we will just have y, b, x, y, and z, and the partial y will be similar but with x, and partial z, because c only the variable, we will have e with power of x, y over z. Okay, so in practice, it actually has a pattern that you can work on, and you can improve that, I believe. Okay. Okay, any question? Okay, if not, then we continue to higher derivatives. I think we will not have a break for online class, I think, and we can have discussion at the end of our class. Okay, now the next part is the higher derivatives. So if f is a function of 2 variables, let's go back to 2 variables. we know that we can take, say, fxy, we can have a partial x, and we can have partial y. Okay, we can have partial x, we can have partial y. Now if we take derivative one more time, take derivative, so derive, which means we have partial x, okay, and partial x, y, or partial y, and partial y, x. Okay, now to make our definition that the partial x, let me write with the bracket to note that we found the partial x, and then we differentiate one more time with respect to x. Okay, that's what it means. It's simply, we can write the definition as this, and we can write in terms of with the second derivative terms, or with z, it's also correct. This is just how to write, and that will be for others terms as well, for xy, yx, yy. Okay. Should be the same thing. So if we have an example, let's take our example. Now if we find it's actually finding, we need to find the second partial derivative. So find second partial derivatives. So first we are going to find the partial x. Maybe we write xy to make it complete. So partial x we derive with respect to x, so 3x squared plus 2x cube, and y will be a constant and 0. And then partial y, or we're going to write partial y here. Partial y, x cubed becomes 0, and this will be 3xy squared, or 3x squared y squared, sorry, minus 4y. Okay, now from here, from this two partial, we derive one more time with respect to x and with respect to y. So we derive with respect to x one more time for partial x. We will get 6x plus 2x become just 1, so 2y cubed. Okay. And then if we derive with respect to y for this partial x, we will have just 3x squared becomes 0, so we'll have 6x y squared. Okay. Now the partial y we derive with respect to y. This becomes 6x squared y. And then minus 4. Okay. And then 4yx. Fyx, sorry, partial y derived with respect to x. this will be equal to 6x y squared, and 4y becomes 0. Okay, now we are going to see some interesting point that these two have partial xy and partial yx, they have the same result. So notice that you have same results for partial xy and partial yx, which is actually our theorem. It's called the Clayroads theorem. Suppose f is defined on disk D that contains point AB. Okay. If partial xy and partial yx both continues on D, then partial xy is equal partial yx. And if you have another order, for example, right, a little bit higher here. So we have another order, for example, partial x, y, y. This means that we will have partial xy and derive with respect to y. Or you can write down and you can write as the third derivative, as a third derivative. And it can be shown that this will equal with okay. I hope if I can have time to prove it, but I think I will prove it later. And from these partials, we can write some particular formulations for we call it partial differential equation. So in calculus 1 you learn about differentials. Now you have partial differential. What differential means, it means that we can express some certain formulation using the notations in the partial world. Okay. And I think in some physics we can apply this partial differential as an equation, like Laplace equations and so forth. But I don't think I will discuss more of that now. Okay, so this will be the chapter 14.3. Okay, this is 14.3, all about the partial derivative. The next section, 14.4, we will discuss more related to geometric view, which we call the tangent plane. The tangent planes. So, similar geometric with what we have seen at the beginning of the class today, and we are going to express how we can make out the plane. Okay, how we can write down the equation for the plane through the surface of the function. Okay. Okay, if you have any questions, you can write down in the chat box. Okay, let me write in the new slide. So this will be 14.4, a tangent plane. Yeah, I hope the delayed writing is not really affecting. Okay, it's just a few seconds delay. Okay, just a review. Okay, just a review. In calculus 1, we have y equal function of x, single variable, right? We have a tangent line. Now in calculus 2, we have at least function of two variables, at least. So by doing this, it shows that we will have a tangent plane. Okay. If I draw, this is actually you can use the same drawing as mentioned before, but if we look here, it's more clear that the T1 and T2, they are making a plane. Okay, so out of T1 and T2, they are making a plane that is touching the surface at point P. Okay, so we can at least write the tangent plane to surface S at point P is defined to be the plane that contains tangent lines T1 and T2. If we let P at point x0, y0, and z0, then if you still remember the plane equation, let's divide all with C. Divide with C. So A over C plus B over C plus Z minus Z0 equal. Now if we write in terms of Z minus Z0, this will turn out negative A over C, negative B over C. Okay. Now negative A over C and negative B over C, let this 2 becomes A, small a, and B, okay, small b. Now we have Z minus Z0, A x minus x0, okay, A minus x minus x0, and then plus B y minus y0. Now when y equal y0, then this will be related to A x minus x0. And when x is equal x0, or maybe to avoid confusions, let me write here and this part here to make it more clear. The Z minus Z0 will be equal to B y minus y0. This is, if you remember the previous part, that we are going to have one variable fixed and one variable as a variable. Okay. Now we can write down A as C minus C0 divided by x minus x0. Same, and then same thing vice versa with B. And thus we are going to have is A. It seems that this has some change in Z divided by change in X. Or if that is very small, we can write as these dou Z dou X as or partial X. And here we can have B as dou Z dou Y or partial Y. Okay. Now from this conclusions, this will imply us that we can write down the equation as this one with A and B as our partial x and partial y. Okay, so let me write a little bit closer here. Let me write let me resize this a little bit here. Resize a little bit here. Okay. Okay, let me write the conclusions and what we have. We can have as an implication. Okay, so suppose f has continuous partial derivatives. Then an equation of the tangent plane to the surface z equal function of x, y, this z to function of x, y, at p 0, y0, z0 is this. Okay. So we can write down the equations and using the partial x and partial y in front of the x minus x0 and y minus y0. Okay, now in practice, actually it's not that complicated. So let me give you a context here, for example. Find tangent plane to the curve v equal to x squared plus y squared at 1, 1, 3. 1, 1, 3, yeah. Okay, maybe giving you some time to write, or you want to try to find in the tangent plane. This is a direct questions to answering. Or to be precise, okay, this is I'm writing the formulations to simplify the partial x, partial y. Partial x, partial y should be also evaluated at that point, that you want to evaluate it, like a tangent, or like usual tangent. You need to evaluate exactly at those points. So we can write actually z minus z0 partial x at this point, and then x minus x0, and then plus the other way around. So let me go a little bit going to the left. Yeah. So we are going to plus partial y at this point. Oh, sorry. Okay. To be clear. Okay, to be clear. So example here. Okay, if we are going to evaluate this, this is paraboloid. It's a parabola for xz and yz is parabola, and it also has an ellipse at the end. It's capped off with an ellipse, so it's elliptic paraboloid. So if we are having our functions as 2x squared plus y squared, then each of partials we can find. So partial x is just 4x, and partial y is just 2y. So at the 1, 1 will be equal to 4. At 1, 1 it will be equal to 2, right? So 4 and 2. So since this is, if we are going to imagine this is x0, y0, and z0 for the point, so what we can do is we can write down z minus 3 because it's z0, and then equal to 4 x minus 1 plus 2, so plus 2 y minus 1 minus 1. So we can write z for x plus 2y minus 2 minus 4, so it's minus 6 plus 3 minus 3 minus 3. And I think if you want to graph from the quadratic surface a function of two variables, I think you can still draw most of the graphs in the GeoGebra, but you need to use 3 dimensions, a 3-dimension graph. Okay, later on I will show you what it looks like, but I think maybe next Tuesday I'll show you. Okay. Any questions so far? Okay. Okay, I think I will give you uh, a graph. Okay. So this is actually the paraboloid that we are evaluating. So this is actually the paraboloid. So this plane here is our z. We go for x plus 2y minus 3. Okay, so this is the paraboloid. Z equal 2x squared plus y squared. Okay. Now, if we imagine, okay, if we zoom in at a particular point, let's say the point P, like this is P, right? The one that we are approaching, 113, right? If we zoom in through this P, if we zoom in, maybe 20 times, 30 times, and if you look this picture, if we zoom in, we are going to have this picture, right? Okay, we are going to have this picture. You see the proportions already differs. We have this the x. We have 4 to -4. We are going to have much smaller, okay, smaller space. So take to more zoom. Okay, so zoom in, zoom in, zoom in. Seems that we have so maybe P is here. So in nearby P, we are having the same plane. It seems it's the same plane. Okay. Now this will give you an idea. You remember that in calculus 1 we have linear approximations. We will also have the linear approximations with the plane, okay, the linear plane. So we will have the idea of linear approximations. So we find from the previous example that from these functions at this point, okay, has a plane z equal for x plus 2y minus 3. So as we can see from this picture, as we zoom in and zoom in when we are evaluating the nearby point of P, then we can say that this L, we can write this plane equation, is a good approximation to the function xy when xy is near 1, 1. And similarly, we call this L as linearizations of f. And we can write down in terms of fxy, approximate 4x plus 2y minus 3. This will be a linear approximation. Or we can also say, because we are in a tangent plane, this is tangent plane approximation. If we are evaluating at point that is near 1, 1, for example, if we evaluating at 1.1 and then 0.95, we will have an approximation of will be around 3.3. And if we are taking this into the function itself, it's quite good approximation. It's quite similar, although it's having some difference in error, but it's small. The error is small. So in general, okay, this is the one that is, I think, essential for you. If we have z, let me write the definition first. Equation of tangent plane to graph of function f of two variables at point A, B, and F, A, B is I hope this not get you confused. This is the same thing. Okay, this is FAB is Z0 actually. So you remember from the previous one. Let me write maybe here. So Z0 we move to here. So that is what we have. Okay. So then this is called the linearization of f at AB, and we linearization. I think linearization we need to make it more. Let me write in more clear way. Okay. It's actually essentially the same, but let me write more clear with terms of L, X, Y. Actually the same thing. And approximation so this is called this is linearization, and this will be the approximation or tangent plane. So linear approximation or tangent plane approximation of f at AB. So basically the idea for the approximation is basically looking at the tangent plane, and from the tangent plane we can have approximation or linearization. Okay, and the key is the point that you want to approximate, that you want to test, should be nearby, okay, nearby the point that easy to be evaluated. And this is only works, okay, so this works if the partial or the function is differentiable. Okay, so when you have the function that is not differentiable, then all of this, of course, right? Of course, that should be an obvious thing to do. Okay, let me give you another definitions on differentials, because we learn the linear approximations and then we need to have more approach on differentials. which means that small numbers that we can compare, and then we can have some calculations. Okay, we can have some example. Okay. Now the definition for the differential: if z is function of xy, z is function of xy, and f is differentiable at ab, and then if we have delta z that can be expressed as we will have a small increment in delta x and another epsilon in delta y. Where the epsilon 1 and epsilon 2 are functions of delta x and delta y, such that e1 and e2, epsilon 1 and epsilon 2, they are going to approach 0 as the delta approaching 0, 0. So what does this mean? Okay. So this definition says that differentiable function for example, the linear approximation is good when xy near AB. So we need to check, okay, whether the function is differentiable or not. Like I mentioned before, it will be not working if it's not differentiable. So another theorem might help us to understand this differential. Okay? So if partial derivatives partial x and partial y okay, the partial and partial y exists near AB and continues at AB, then f is differentiable at AB. So we will know that the function is differentiable or not Okay, so we'll know the function is differentiable or not at this point AB if the partial derivative exists and it's continuous. Okay. Now is the screen still clear? I believe I have some connection problem before. Can you still hear my voice or no? Okay. Okay, now if we look back in this epsilon 1 and epsilon 2, this just suggesting that we will have a small error, okay, and if this is very small and we are going to have the limit as our tools, we can ignore some small error, right? But still we need to write this epsilon in terms of differential. And we can write the differentials in terms of, we write the differentials and write the differentials as or this is dou z dou x dx plus dou z dou y dy, and we define this as a differential. And then we can also take some graphs to differentiate. Okay, now if you see this graph, although it seems really complicated, I believe it's still inconsistency. Inconsistency. Let me put maybe here. For example, you need to be aware of the delta z that we are approached before is actually the real distance, the real distance from the surface to the point that we are going to approach. And the dz is actually our tangent plane, our let's say the linear approximations, right? The tangent plane. So I think the most notable or essentials is this these two different distance for delta z and dz. Okay, if you look on the other sides, the delta, they are, we can make them into equal. Because the way that we are seeing is the height will be different. Okay, the height will be different. Okay, I think 14.4, yeah, we finish 14.4. I will let you know some of the examples. Okay, but let me give you an example. Example for approximations, for linear approximation. Let me give you an example. Okay, show that partial xy, function xy equal x is differentiable at 1, 0, and then find linearization, then use it to approximate first. What we are going to do, we are going to evaluate the partial x and partial y. So first, this is the function. So we derive for with respect to x, so partial x. This will be equal to, using the product rule, okay, this will be having two functions there. Two functions x and e to the x, y, and y will be treated as a constant. So partial x will be e xy plus x and then y and then e xy. Okay. And we can evaluate at 1, 0. It's becoming 1, and the other with 0, so it's 1. Okay. We can also evaluate the function itself at 1, 0 if you want. This will be equal to 1, right? And partial y, we can also check that off. So we will have x, and then multiply with x, becomes x squared, okay? And then e, and then x, y. We check this with 1, 0. Check with 1, 0, and it's also 1. From these two, we see that both partial x and partial y exist and continue at 1, 0. Now linearization. Okay, for 1, 0, we can check. This is 1 plus x minus 1 and plus y. So we can simply write down that this is x plus y, the linearization. From the linearization, we can check our point, that is 1.1 minus 0.1, which is approximate 1. We can check the true value. f1.1. We can check the true value. So 1.1 e 1.1. If we check with calculators, this will result in 0.98 something. So actually, it's close, right? It's close to the real value, and the difference will be the error. That will be the error. And I think I will just stop here, okay? And we'll continue later on next Tuesday, and also I will maybe getting some feedbacks from you for chapter 14, especially to see whether you are at least the basic understand. So if there's no questions, then we will just finish up until here. So if you have any questions, please let me know. And if not, then you can free to leave the meetings. Okay. If you want to have the QR code scan, you can scan the QR code. Okay. Okay, so if you finish, you can leave the meetings. Okay.